Hi everyone. So my first recording for this week is going to be on the topic of reflection and disagreement, and I'm going to take the same approach that I did for the last recording, which is to base what I'm going to say on the extended handout, which is on Moodle, um, and I'll try and explain a few points that might not be obvious from just reading it, and maybe elaborate on some others. So here goes. So if you recall from right before reading week, we talked about subjective Bayesianism and objective Bayesianism, and the idea that the objective Bayesian takes there to be constraints, objective constraints on an agent's prior probability distribution. Um, the subjective Bayesian thinks anything goes, provided the agent at all times has credences that obey the probability calculus and responds to evidence by conditionalization. Then that is sufficient for rationality, whereas the objective Bayesian demands more. So one principle that someone of objectivist leanings might appeal to, we saw, is the principle, which says that an agent, a necessary condition for an agent's rationality is that if they, sorry, I should say, if their credence in a proposition A, conditional upon the chance of A's taking some value, ought to also be equal to that value. So if they can, if they're interested in the proposition that a particular die comes up 6, then their credence in the die coming up 6, conditional upon the fact that the chance of its coming up 6 is 1/6, or to also to be equal to a 6th. So there's a bit of complication around so-called admissible evidence, which we went through when we discussed the principle, but that's the principle in outline. Now, for the objective Bayesian in particular, or someone who tends that way, that they might devise other principles concerning what an agent's prior probability distribution ought to look like. When it comes to chance, the principle rule obviously says that you should sort of defer to what the chances are when setting your credences. Now, in a way, that's kind of like taking the chance function to be an expert. So if you know what the chance is, then you ought to adopt that as your credence. There are other sorts of kind of what we might call expert probability functions that you ought to defer to in setting your credences besides the chance function. So, for instance, a human expert, such as a weather forecaster, they're presumably expert on what the weather's going to be like. So, for instance, if I know, just as if I know what the chance of the weather being sunny is, then I ought to adopt that as my credence. Likewise, if maybe I don't know the chance, but I know that the credence that the weather forecaster assigns to it's being sunny, then it appears that I ought to adopt the weather forecaster's credence as my own. Now, another sort of interesting category of sort of expert function is discussed by Bas van Fraassen, and he suggests that just as chance is an expert, and people like weather forecasters are experts, at least with respect to their particular domain, you should also take your future self to be an expert. So he captures this via what he calls the reflection principle. So let P1 be your credences at some earlier time, and P2 are your credences at some later time. Then suppose that your later credence in some proposition A is equal to X, then Van Fraassen advocates the reflection principle, which says that your credence at the earlier time in A, conditional upon the proposition that your credence at the later time in A is X, ought also to be equal to X. So you defer to your future self's credences, just as, say, the principle has you defer to the objective probabilities in setting your credences. So we might regard, and Van Fraassen regards, this reflection principle as a principle of rationality. Now, why should we believe the reflection principle? Well, a key reason is that we might think of ourselves as acquiring more and more evidence over time. So the idea is that your future self is going to be more informed about matters than your present self is. And therefore, one ought, if one somehow knew one's future credences, to adopt them right away as one's current credence. Now, I suppose there's something a bit puzzling about the reflection principle, because you might simply think, well, that's great, but I don't know my future credences. Well, I mean, that's true typically, that we don't know what our future credences are going to be. But it's worth noting that there's a sort of more generalized version of the reflection principle that actually follows via the theorem of total probability, and says that your current credence should be equal to your expectation of your future credence in the proposition. So this is just like where you don't know the chance, your credence ought to be equal to the expectation of your expectation of what the chance is. That is to say, it ought to be equal to the possible values of the chance, weighted by the probability that you currently assign to those values being the chance. So when it comes to reflection, the idea is similar. The idea is that your present credence in A ought to be equal to a weighted sum of the possible values of your future credence in A, where the weighting is done via your present credences that those will be your future credence. So this is your present credence in A, and the equality says that what we want to do is we want to take each of the possible values of your future credence in A, so these are represented by the xi's, and we want to multiply them, essentially weight them, by your current credence that your future credence, your P2 or your time 2 credence, will be equal to that value. And if we do that for each possible value xi of your future credence and sum them all together, then that gives the expectation of your future credence in A, and the generalized reflection principle says that your current credence ought to be equal to that. Okay, so it's sort of interesting, the reflection principle. There are some problems with it, even to the extent that we think it's going to be applicable or useful. But but it's just another example of the sort of case in which we might think where there are experts that need to be deferred to. So chance, the weather forecaster, maybe an economist about economic matters, a doctor about medical matters, and generally one might think one ought to defer to one's future self if one knew one's future self's opinions, or at least had expectations about them. But actually, before I come to problems for the reflection principle, it's worth saying that there's a question about what to do when you find out the opinions, the credences maybe, of people who are non-experts. And that's what we're going to be mostly focused on this week. So what do you do when you meet someone who's informed about a particular matter, but is not someone you necessarily want to completely defer to, right? So you might have some independent information, or you might have some confidence in your original credences, that mean that maybe you shouldn't simply defer to them or treat them as an expert. And we're going to come back to that topic shortly. But let's first think a bit more about the reflection principle. So how plausible is it? Well, it seemed to derive its plausibility, or whatever plausibility it had, from the idea that one simply gains more information over time, more evidence over time. And so one's future self simply knows more than one's current self. So it would be better to have one's future self's credences than one's present credences. But there are at least two problems with this assumption that your future credences are somehow better or incorporate more information than your present credences. The first is that you might actually forget things over time. So you don't strictly just gain evidence over time. You sometimes lose evidence. So I think there are fairly straightforward examples of this. So it happens that I was outside in Cambridge yesterday, which is where I live, and I observed it to be sunny. So consider the proposition. It was sunny in Cambridge on the 22nd of March, 2020, which is yesterday's date as I speak. Now, I think that probably in 10 years' time, I'm going to have virtually no idea what the weather was like on the 22nd of March 2020. I just won't remember. So then, in 10 years' time, my credence in this proposition will probably just be roughly equal to whatever I think the relative frequency of sunny days in Cambridge is, or maybe sunny mid-March days in Cambridge. And that's going to be a lot less than 1, so it's not true that 100% of days in Cambridge, or mid-March days, are sunny. So it might be something like 0.25, but it seems fairly evident that my current credence in A, conditional upon my future credence being around 0.25, shouldn't be 0.25. So, in other words, conditional upon the fact that my future credence in 10 years' time, that it was sunny in Cambridge on the 22nd of March 2020, is 0.25. Shouldn't be 0.25, rather it should be almost 1, since right now I plainly remember that it was sunny. So actually I'm have more evidence, you might think, than my future self about what the weather was like yesterday. And that's because my memory is imperfect. So I will sort of lose that evidence or information that I currently have in 10 years, within 10 years. Okay, so another sort of reason to be a bit skeptical about the reflection principle is that you might think that your future self will have irrational beliefs, So it might not simply be a problem that they lose evidence, they forget things, but they might actually form irrational beliefs too. So an example now I'll give is suppose that I have a credence right now of zero point 0.3 that the team I support will win the FA Cup next year. I say on the handout, suppose I'm planning to go to the pub tonight. I guess in the current circumstances, maybe I'm planning to FaceTime a few friends and drink on my own while I FaceTime them. But I know that after a couple of drinks, I tend to get very over optimistic. Now, consider the proposition that my credence that my team will win the FA Cup I should say this again. Suppose that consider the proposition that my credence tonight of my team winning the FA Cup is 0.9. Well, it seems that my present credence that my team will win the FA Cup, conditional upon my credence tonight being 0.9, should be 0.9. That doesn't seem right at all. Rather, it should actually be close to whatever my current credence is. I know I'm going to be irrational tonight, so I shouldn't have a credence conditional upon tonight's opinion that varies much from my present opinion that I consider to be the rational one. Okay. So, I suppose you might argue that an ideal agent should obey reflection. So maybe an ideal agent doesn't forget anything and never changes their beliefs in irrational ways. So, for instance, in the second example, the idea is that I wouldn't have changed my belief in my team's winning the FA Cup in a rational way, so I wouldn't have conditionalized upon any evidence. In fact, probably I don't really gain any evidence between now and tonight. I just have a few drinks, which changes my degree of belief, but it's not a rational change of degree of belief. It's not a change that results in responding to evidence via conditionalization. So maybe an ideal agent would always remember their evidence and respond to it via conditionalization. But then again, we run into this sort of issue that we frequently encounter with formal epistemology, and that is that, well, okay, maybe that's the right prescription for an ideal agent, but obviously we're not ideal agents, so to what extent is this actually a useful epistemic principle? Now, the topic of peer disagreement, which is the sort of major topic for this week, is interesting for a number of reasons. So firstly, we're going to look at cases where other people have opinions that you think you might respond to, but you don't treat them as experts. We'll see actually that this interacts with the question of ideal rationality versus bounded rationality quite significantly. So we'll see that actually thinking about what one should do when one encounters these sorts of people actually yields some useful prescriptions, or potentially useful prescriptions, for people like, I presume, all of us to be boundedly rational agents, not perfectly rational agents. So the concept of an epistemic peer is someone, maybe a friend of yours, who is roughly of equal intelligence and has maybe the same evidence as you are about something, or maybe different but equally good evidence. We'll suppose for simplicity they have exactly the same evidence as you. So if they're as intelligent as you and they have the same evidence, then we call them an epistemic peer of yours. Now, things might be a bit more messy in real life because you might the sort of people you encounter, you presumably won't always think of the same intelligence as you, and sometimes you'll think maybe they have a bit more or a bit less evidence. Even if they don't have so much evidence, you're going to treat them as an expert and just defer to them entirely. We'll come back to some of these issues as we go on. So, but first make the simplifying assumption that we're dealing with an epistemic peer. So an example would be you and your friend, your equally intelligent friend, go to the races. You're both equally expert about racing and about horses. You're both equally good at statistics. You've read the same form guides, you know the same information about track conditions, the conditions of the horses, and so on. And not only do you each have the same abilities and have the same evidence, but you also know the other person does. So you both know that you have both have the same abilities and evidence. So the problem then is what to do if your credence then diverges. So suppose that before the race, you tell each other what your credences are that a particular horse, Norse King, will win the 3:15 race. Suppose that your credence is 0.3 and your friend's credence is 0.2. Then what should you do? That's the question. Now there seem, I guess, two sort of obvious suggestions, although they're incompatible with one another. So there's a sort of steadfast view which says just stick to your guns, continue to assign credence 0.3 to Norse King winning. We'll see some motivation for that shortly. And on the other hand, there's what's known as the linear averaging view, sometimes called the equal weight view, which essentially says you should take the mean of your credence and your friend's credence and adopt that as your new credence. So the idea is you basically split the difference between your credences to arrive at a new credence that takes into account your friend's view. Now, so this second proposal, the linear averaging proposal, is often motivated by the idea that, well, really there's nothing better about your credence than your friend's credence because it's based on the same evidence, the same intellectual capacities, and so on. So, in light of that, one might argue that it's just irrational to sort of stick to your guns and act as though somehow you're special or your credence is special. And so the idea is that given their equally good provenance, you should equally weight these two credences. And an obvious suggestion for doing so is to split the difference between them in arriving at an updated credence. Now, okay, what about the steadfast view? So that's some initial motivation for the linear averaging view. What about the steadfast view? Well, the steadfast view might seem attractive if you're confident that your initial beliefs were reasonable, so your prior distribution was reasonable, and that you've updated via conditionalization. Then, the sort of motivation is there's nothing wrong with your views, so why should you change them in response to what your friends' views are? So, I suppose that this is quite plausible on, or at least more plausible on a Bayesian view, where the version of Bayesianism is a kind of subjective leaning one. So it might be that you had your prior distribution, your friend had their prior distribution, each of you has the same evidence, each of you updated on that evidence via conditionalization, well, suppose you rationally updated, then the reason that you still differ in your credences for Norse King winning is just because your prior distribution was different, your prior probabilities were different, and because they were different, that led through into different posterior probabilities, even though you conditioned on the same evidence. Now, the subjective Bayesian might say, well, there's nothing wrong with this doesn't show there's anything wrong with your prior distribution, or your friends, in fact, provided they were probability distributions, they obeyed the axioms of probability. Both of your prior distributions were perfectly fine, even if they differed. And given that you both updated on your evidence via conditionalization, there's nothing wrong with your posterior degrees of belief either. So there's nothing wrong with your credence, nor is there anything wrong with your friend's credence. But there's no reason to move in the direction of their credence, simply because there's nothing to fault your own. It just reflects your difference in prior probabilities. Now, okay, so I suppose objective Bayesians might not be so persuaded, because they might think that, well, there are sort of objective constraints on prior probability distributions, and so they might think, well, it's plausible that the differences in your priors is an indication that at least one of you's got the priors wrong, failed to meet the objective constraints on the priors. But independently of that, I mentioned real life kind of boundedly rational agents earlier. We might wonder about those sorts of people. So real life agents like us, who, might not be sure that we've always updated via conditionalization assiduously throughout our lives, and so we might, given that we're non-ideal agents, in fact, take the fact that our friend's credence is different from our own as a sort of evidence that actually we've messed up, right? So as a real life agent, suppose you have the same evidence as your equally intelligent friend, but you learn that they've arrived at a different probability judgment or a different credence from you. So that at least raises the possibility that one or both of you has kind of messed up in their reasoning about their evidence. And if you can't, it's very difficult maybe to perfectly check the reasoning if you don't have a way of sort of checking the reasoning, then you might think that so to identify which, if either of you was at fault, for instance, if you're not able to go back to your both of your baby priors and do all the think about what would follow from conditionalizing on all your evidence again, then it might seem that the different splitting strategy looks better. So you might think, well, okay, at least one of these credences is wrong, has resulted from some mess up. Maybe it's kind of unlikely that we've both messed up, given that we're both pretty intelligent. So you might think, well, we can't tell which one of us has messed up. So if we split the difference, that'll, while it'll mean that neither of our credences is perfect, we're at least ensuring that neither of our credence is too far away from what our credence should be. So you might reason that's the way. We'll look more closely at the linear averaging view shortly and see that there are some issues with it, unfortunately. So before we do so, it's worth noting, and this might hopefully help clarify some of the discussion so far, a distinction that I think is helpful between what might be called first order evidence and higher order evidence. So this is sometimes distinguished by philosophers in this sort of context. Bradley, who hopefully you've read on this topic, distinguishes opposing versus undercutting defeaters. That distinction is roughly along the same lines. I prefer the first order versus higher order distinction for present purposes. So I described the sort of evidence that you and your peer have regarding this race. So your knowledge of horses and horse racing, your knowledge of the track conditions, of the form of the horses, and so on. I've supposed you both have exactly the same evidence for simplicity, and I labelled that evidence E. So that is your first order evidence, just regular evidence about which horse is going to win. Now, the idea when it comes to higher order evidence is that higher order evidence is evidence about how well you've evaluated your first order evidence, your regular evidence. So the suggestion is, at least for boundedly rational agents, finding that we disagree with an epistemic peer provides us with some higher order evidence. It provides us with some evidence about whether we've correctly evaluated our first order evidence. In particular, if you find that an epistemic peer agrees with us on their probability assignment, that might support the notion that I've correctly evaluated my first order evidence. But if my peer disagrees with me, despite having the same first order evidence, that might raise my credence that I've in fact responded incorrectly to my first order evidence. Now, I guess this might not apply to an ideally rational agent. So maybe an ideally rational agent knows that she always perfectly evaluates her first order evidence. But it does seem like the sort of consideration that might apply to beings like us. Okay, so you might think that, well, for beings like us, acquiring higher order evidence, and not just acquiring first order evidence, can and should lead us to revise our credences sometimes. And that, I suppose, is one way of motivating the linear averaging proposal or something like it. So we've got this, our first order evidence remains the same, all the stuff to do with the horses and the track conditions and form and so on. But now we've gained some evidence that maybe we've messed up when evaluating that first order evidence. And maybe given that judgment that it looks like at least one of me and my peer have misevaluated, maybe we should each move in the direction of each other's credence to limit the error. Okay, so just to be a little bit more formal, so the basic linear averaging proposal is that on learning an epistemic peer's credence in a proposition A, one's updated credence ought to be just the mean of the two original credences. So this is represented in the equation here. I'm supposing that P1 is my credence, P2 is your credence in this proposition A, and that we're epistemic peers. And these are our initial credences before we that we report to each other. And the idea is that once we've reported them to each other, then each of us ought to respond to that by adopting a new credence in A that's equal to the mean of our all credences in A. So in other words, we just sum the credences together and divide by the number of agents, which in this case is 2, but obviously you could generalize it to a case where there are multiple peers. You just divide by the number, sum all the credences together and divide by the number of agents to give you the mean. Obviously, this is equivalent to this expression here, which says, again, is just an expression for finding the mean. This expression, there's something to recommend it in that it sort of makes obvious that the post-update credence, according to this linear averaging view, is equal to the sum of our, or the sum of our prior credences weighted by a half, right? So we're treating each of our prior credences as kind of equally good. We're giving them equal weight. So that's why it's sometimes known as the equal weight view. Okay. Now, I mentioned earlier that, in real life, we are often going to be in a situation where, our friends or the people we meet, whilst we don't regard them as complete experts, so we don't defer to them entirely, we also don't regard them as perfect epistemic peers. So you might think either that they're more knowledgeable or intelligent than you, or that you're more knowledgeable or intelligent than them, at least a bit. And so if that's the case, you might think that simply exactly splitting the difference isn't the right approach. So you might want to give a bit more weight. So if you think you're a bit better than them, you might, for instance, want to give a bit more weight to your original opinion. So a sort of natural generalization of this sort of equal weight view is just where we adjust the weights. So in the basic linear averaging proposal, the idea was to just incorporate equal weights of a half, where there are two agents. To give equal weight is to give each a weight of a half. In the two-agent case, the idea is, in general, we could take your updated credence, or we could recommend that it be a weighted sum of each of the two agents' reported credences, where the weight's given by W1 and W2. W1 and W2 have to sum to 1 in order to be sure that this returns a probability. But the values of W1 and W2 could differ from a half, right? So if you thought that you were a bit better, or your opinion was a bit better than your friends, then you could increase this and W1 and decrease W2. So maybe W1 could be 3/4 and W2 1/4. Okay. All right. So and I mean, this just generalizes to the case of multiple peers. So again, we're going to be looking at a weighted sum of their reported opinions. So the suggestion would be that your updated credence ought to be a weighted sum of the original opinions of all you and all of your peers, and the weights have got to sum to 1, but perhaps they needn't all be equal. Perhaps you regard some of your peers' opinions as better than others. Okay. I mean, I guess maybe I should say friends rather than peers. In a sense, peers is often used to have this technical meaning in this literature to mean people who are exactly as good as you. I've been a bit sloppy in sometimes using peers to more liberally to also mean people who are sort of in the same ballpark, good as you, but might still deserve slightly different weighting. Okay, so I think there's quite an intuitive pull to weighted averaging of some sort, linear averaging. Um, and it's certainly quite a popular view in the literature on peer disagreement. But there are actually several problems with it, and I suppose sort of the cutting edge of this literature is really discussing some of these problems, weighted averaging, which seems the natural sort of proposal, or maybe a natural proposal, and then trying to devise responses or rules that produce better outcomes than linear averaging. And I'll look at one such rule that arguably does at the end, just as an example. But obviously, there's more available on the further reading list. So one problem, I mean, in a way, some of the problems are quite technical. This is quite a technical problem. Maybe I won't go through all of the calculations in sort of laborious detail. It might be easier for you to go through the handout and check my working and make sure you understand it on your own and let me know if you've got any questions about it. I'll go through it to some extent. So the example is, suppose that you and your peer, epistemic peer, each have credences concerning whether it's going to rain in Bloomsbury tomorrow. Suppose you assign a credence of 3/4 to it's raining. Your peer assigns a credence a half to it's raining. And suppose separately you and your peer also have credences about whether a Democrat's going to win the next US presidential election. Maybe you assign credence a half to a Democrat winning, while your peer assigns a credence a quarter to a Democrat winning. Now, let's suppose that both you and your peer, what you do agree upon is that whether it rains or not in Bloomsbury tomorrow is completely irrelevant to whether a Democrat will win the next US presidential election. Right, okay, so where events like this are independent, you can easily calculate the probability of both obtaining just by multiplying your probabilities that each of them obtains. So you regard rain in Bloomsbury tomorrow as independent of whether a Democrat wins. So if we want to calculate, so P I'm taking to be your credence function, and Q is your peer's credence function. So if we want to calculate the probability that you assign to it raining in Bloomsbury tomorrow and a Democrat winning, given that you regard these events as independent, we just multiply your credence that it rains with your credence that a Democrat wins. So in other words, 3/4 by half, which gives us 3/8. And then we can do this for all combinations. So your credence that it rains and a Democrat doesn't win is just going to be your credence that it rains multiplied by 1 minus your credence that a Democrat wins. So 1 minus a half is a half. And so we get this result 3/8 again. And similarly, we can calculate your credence that it doesn't rain and a Democrat wins, and that it doesn't rain and a Democrat doesn't win. So we get this distribution over the partition defined by these two events. And we could do the same for your friend, calculate their joint probabilities for rain and a Democrat wins, rain and a Democrat doesn't win, no rain and a Democrat wins, and no rain and a Democrat doesn't win, just in exactly analogous fashion. The values are obviously a bit different from yours because you each assign different credences to the proposition that it rains and also to the proposition that a Democrat wins. Okay, so the next thing is to suppose that you each now discover each other's credences for these four basic possibilities, reigning Democrats wins and so on. And maybe you both think that linear averaging is the right way to go when you find out that you disagree with your peer. And so what you do is you basically, in order to arrive at an updated credence that it reigns and a Democrat wins, so the updated distribution is going to be represented by O. What the idea is to arrive at that, you're going to take the average, the mean. We'll suppose we're weighting each equally. The mean of your credence that it reigns and a Democrat wins, and your friend's credence that it reigns and that a Democrat wins. And so the average of 1/8 and 3/8 is 2/8. And likewise, we're going to do so for all the other combinations. So this would be the updated credence distribution that would arrive at if we had those initial credences and updated by taking the mean. Or in other words, weighted linear averaging with equal weights. Now, the problem with this is that the updated credences that you arrive at don't treat the two events as independent, right? And so basically the way we can see this is by considering the theorem of total probability. So according to your updated distribution, the updated credence that it reigns is equal to the updated credence that it reigns and a Democrat wins, and that it reigns and a Democrat doesn't win. So that's just the theorem of total probability. So assuming obviously you obey the probability axioms, then this calculation applies. Your updated credence that it reigns and a Democrat wins is 2/8, and your updated credence that it reigns and a Democrat doesn't win is 3/8. So we get a solution of 5/8. And likewise, you can calculate the updated probability that a Democrat wins via the theorem of total probability by summing together your updated credence that it reigns and a Democrat wins together with your updated credence that it doesn't reign and a Democrat wins. And so reign and Democrat is 2/8 again, and not reign and Democrat is 1/8. So we get the result 3/8, which is approximately 0.375. Okay, so that's the updated credence that a Democrat wins. Now we can also calculate the conditional probability according to your new credence distribution that a Democrat wins conditional upon it reigning. And we just use that by applying the usual definition of conditional probability to our new probability distribution. So the updated credence in it reigning and a Democrat winning divided by the updated credence in it reigning gives the updated credence in a Democrat winning conditional upon it reigning. So we just do the calculations and we wind up with 0.4. But note that this implies that the updated credence distribution doesn't take the two events as independent. That's because the value of this, the credence that the Democrat wins conditional upon it reigning, is higher than the unconditional credence assigned to a Democrat winning. So this is actually this is an expression of non-independence, of probabilistic dependence. It says that a Democrat is more likely to be the next US president, conditional upon it reigning tomorrow. And you can easily calculate, if you want the probability of a Democrat winning conditional upon it not raining tomorrow. And if this holds, you can easily show that the probability of it raining conditional upon, a Democrat winning conditional upon it raining is going to be greater than the probability of a Democrat winning conditional upon it not raining. Now, this is problematic because both you and your friend originally agreed that it was the weather tomorrow in Bloomsbury was completely irrelevant to whether a Democrat wins, and yet you've updated by linear averaging, and the upshot is that your new credence distribution says that it's more likely that a Democrat will win if it rains tomorrow in Bloomsbury. And so the updated distribution seems irrational in light of the prior distributions. And note that this is quite bad because, if you actually had these credences and someone offered you a bet on whether a Democrat will win and you didn't know what the weather was in Bloomsbury, then this implies you'd be willing to pay somebody money to find out what the weather was in Bloomsbury before deciding to take on the bet. So if the bet was very high stakes, you'd be willing to pay someone a moderate amount of money to discover what the weather was in Bloomsbury before taking on the bet. And again, that seems irrational. Okay, so and playing around with weights, it turns out, doesn't help with this unless the weights are 1 or 0. That is to say, unless you're steadfast and stick to your own original opinions, or you completely defer to the opinions of the others. Generally speaking, it's going to be the case that agreements on independence between you and your friend are not going to be preserved when you update by linear averaging. Okay, so that's rather technical problem, but quite a big problem. Another sort of kind of technical, but a bit easier difficulty is that linear averaging isn't associative. What that means is that what order you meet peers in matters to your final credence. So the example I've given on the handout is, suppose you have credence half that is extraterrestrial life, maybe intelligent life, let's suppose. Susie, who's one of your peers, has credence 0.2 in this. Billy, another of your peers, has credence 0.7 in this. So suppose you talk to Susie about the question first, and you take the linear average of the two credences, your initial credence and hers, which gives you a result of 0.35 being the mean of 0.5 and 0.2. And then suppose that you next meet Billy, and you take the linear average of your new credence of 0.35 and his credence of 0.7, then you get the results, the super new credence of 0.525. But suppose you'd met them in the reverse order. Suppose you'd first met, or at least discussed the issue with Billy, and so you've taken the linear average, or the mean of your initial credence of 0.5 and his initial credence of 0.7. That will give you a revised credence of 0.6. And suppose that you'd met and discussed the issue with Susie second, who has credence 0.2, and take the mean of your new credence of 0.6 with her credence of 0.4. Oh, sorry, with her credence of 0.2, then this would give you, have you ending up with a credence of 0.4 as opposed to 0.525. So there's a significant difference between the credences that you arrive at following the linear averaging proposal, depending upon the order in which you meet your peers. But that seems bizarre because it doesn't seem like the order in which you meet your peers will generally, or the order in which you discuss the proposition with your peers will generally constitute evidence about whether there's extraterrestrial life. Okay. So Now, I suppose there's some sorts of kind of responses to this that one might adopt. So you might think, well, maybe the right thing to do is each time you discuss the proposition with another peer to go back to your very original credence and average against the values of the credences of all the peers you've so far discussed it with, right? So you might, rather than, you might average with Susie first, but then when you discuss it with Billy, the idea is you wouldn't then average your new credence with that of Billy's, but you go back to your original credence and take the mean of your original credence, Susie's credence, and Billy's credence. And then the order in which you met the agents wouldn't matter. Now, okay, so that seems like a kind of reasonable proposal, at least at first glance. One issue is that it is quite challenging for ordinary agents to implement this, right? So, perhaps you're super interested in, alien intelligence, and you join on all the conventions of people with similar interests, and so you're frequently discussing the topic with people who qualify as epistemic peers of yours, and they all have different credences. You're supposed to remember your original credence and all of the credence reports you've heard from everyone throughout your life, so that you can conduct this averaging every time you discover a new credence report. So it's quite demanding. There's also sort of another issue, which is that what if you acquire evidence between the time that you meet your peers? So between meeting Susie and Billy, you might learn that NASA's just discovered an extra 1,000 planets that have good conditions for intelligent life to evolve. Now, it's just sort of unclear what to do then, right? So it seems like you shouldn't completely retreat your original credence. You want to take into account this extra information. But what if Susie has this information and Billy doesn't? It basically gets a bit messy, and it's not clear exactly what the prescription should be. Okay. But, I suppose that, you might think maybe there is some solution. Maybe you can play around with the weightings. So the fact that Susie didn't know this information, maybe you should give her credence lower weight, or something like that. So, okay, maybe it is a sort of pragmatic problem, but the independence problem does look like a real difficulty. So you might think, okay, all right, so linear averaging kind of looked kind of nice, but it runs into some problems. But you might think, well, why are we even doing this, right? After all, we've been given a perfectly general, perfectly reasonable seeming rule for updating upon evidence, namely conditionalization, one that we encountered very early in terms. So you might say, well, forget all this linear averaging and so on. The way in which you should actually respond to learning the credences of your peers is just by conditionalizing on them. Suppose that your peers' credences are represented by the function designated Q, yours represented by a function designated P. You learn that your peers' credence in some proposition A is equal to X. Then the idea is your updated credence in A ought to be equal to your prior credence in A, conditional upon the proposition that your peer's credence in A would be equal to X. Now, I suppose that maybe there are a couple of issues with this. So one is that it's, again, quite demanding for agents like us, right? So so in order to do this, you need to have a prior credence that takes this form. And it seems that in order to do this generally, you'd have to have this sort of prior credence for any possible epistemic peer you might meet. And note that if you're not particularly expert on a topic and you just meet somebody randomly, and you find out their credence on something and you don't particularly know much about their background, then because you're not an expert either, it might seem reasonable to treat them as though they were a peer because you're not sure whether they're the same as you, or more expert or less expert, but you have no reason to think they're more expert than less expert or vice versa. So it's kind of plausible you should treat them as a peer. But do you really have, a credence that there's intelligent life conditional upon some person in the street saying there's intelligent life? Maybe a regular agent doesn't have credences like this in their prior distribution. Okay. Yeah, and then I suppose sort of so it's linear averaging seems like a simple proposal, but maybe there's something more significant, which is that linear averaging was partly motivated by thinking about what non-ideal agents should do, right? So if you're an ideal agent, maybe you just know that you've evaluated your evidence correctly. So why should you change in response to learning the credence of somebody else? Now, a non-ideal expert might not be certain that they've evaluated their own evidence by conditionalization, or at least that they've not done it properly. Now, the question is whether, if you've failed to conditionalize in the past, so or at least if there's a possibility that you've failed to conditionalize, that is, if there's a possibility that you've failed to rationally update on your evidence in the past, is conditionalizing on your friend's opinion going to remedy the problem? Right? Not necessarily, because if you have what seems to be an irrational prior distribution, or one that hasn't properly incorporated your evidence to that point, then updating on some new evidence by conditionalization isn't going to necessarily help fix that, right? So the irrationality of the prior distribution is liable to feed through into irrationality of the posterior distribution. So whereas there's a sense in which linear averaging, there was a sort of rationale for that, where you weren't sure about the rationality of your own prior credence, because the thought was that it's unlikely that both you and your peer will have messed up, and if you split the difference, at least you'll make sure that neither of your credences is too far from what it should be. Okay. All right, so much for conditionalization. Now, I said there are some sort of alternative rules that are maybe a bit don't suffer from some of the problems that linear averaging does, and that maybe also avoid some of the issues that boundedly rational agents have when it comes to conditionalization. One rule, which is rather complex, or at least superficially so, that's been proposed in the literature is a multiplicative rule. So this reading is on the further reading list, so I suppose especially if you sort of enjoy technical stuff, this might be appealing. I don't need to go into it in great detail. It's not sort of like, unless you particularly enjoy technical stuff, then it's not super necessary to understand all the ins and outs of this. It has this form. So in the two-agent case, it says that your updated credence in some proposition A when you learn the credence of your friend. So P1 is going to be your credence distribution, your initial one. P2 is going to be your friend's initial one. Then it has you arriving at an updated credence via this formula. So it's the numerator is the product of your initial credences, and it has you divide by the product of your initial credences plus the product of 1 minus your initial credences. So yeah, I mean, if you want more details on what motivates that rule, then it's worth looking at the reading. And it's shown in that paper that this rule is associative, so the order in which you update doesn't matter. The order in which you discuss these issues with your friends doesn't matter. It does a better job of preserving independence than linear averaging, and actually it approximates conditionalization in a range of cases, but is maybe a bit less demanding. So I won't go through all of these issues that they're outlined in the paper. But what I would like to draw your attention to is a particularly interesting feature of this rule that linear averaging lacks, and that might be a sort of intuitive way of sort of evaluating some rule like this versus linear averaging. So in particular, note that if you adopt a linear averaging proposal, then your revised credence upon meeting your peer and updating is going to lie between your original credence and your peer's original credence. It's going to be in between the two. Even if you're steadfast, it doesn't lie outside that interval between your credence and your peer's original credence. But arguably, sometimes it's rational upon meeting even an epistemic peer, to move to a credence that is even higher than, or even lower than, either of your two initial credences. So the epistemologist David Christensen gives the following example. He says, suppose that I'm a doctor determining what dosage of a drug to give my patient. I'm initially inclined to be very confident in my conclusion, but knowing my own fallibility in calculation, I pull back a bit to a credence of 0.97. I also decide to ask my equally qualified colleague for an independent opinion. I do so in the conciliatory spirit of using her reasoning as a check on my own. Now, suppose I find out that she has arrived, presumably in a way that also takes into account her fallibility, at a 0.96 credence in the same dosage. Here it seems that the rational thing for me to do is increase my confidence that this is the correct dosage, not decrease it as difference splitting, or in other words, linear averaging, would require. So his idea is that you're already very confident in a particular dosage as being the right one. Now you've learned that your peer is also very confident that this dosage is the right one. So actually you shouldn't reduce your credence that the dosage is the right one towards hers, which is slightly lower, but actually increase it still further. Now, linear averaging isn't going to give you that result. So if you linear average with equal weight, you're going to arrive at a credence of 0.965, which is halfway between your original credence and your peers. And generally, if you with weighted linear averaging, it's going to be somewhere between 0.96 and 0.97. But Christensen thinks that's the wrong result. And this multiplicative rule that I just described actually gives the sort of verdict that Christensen seems to think is rational. So we just basically plug in the values. So 0.97 being your original credence, and 0.96 being your peer's original credence. So we plug in the values all the way through, and the result is an updated credence of 0.9987, which is higher than either of your original credences. So this at least gives you this result that some people have called synergy. So where your final credence is higher or lower than any of your peers or your own original credences. So just to sort of draw all this together, I think kind of there's no real consensus at the moment in the peer disagreement literature. It's a very lively and active field of research. Actually, interestingly, several people in the UCL philosophy department have written on this topic, but more generally, in global terms, it's a very significant area of current research, especially in formal epistemology. Um, and I mean, it's kind of quite profound consequences because we might be interested in, for instance, when we've got equally qualified experts advising the government, maybe on something like climate change, and they give different probability assignments, they could be regarded as peers. And the question is how to devise or how to arrive at a sort of agreed probability from their initial probabilities. That might be like the peer disagreement problem. So there's a lot of lively debate on this in the literature and there's sort of different rules that have been proposed. I've given a few examples, but none has yet reached, I think, the status of general orthodoxy or general acceptance. Some of the other proposals can be found by looking at the readings on the further reading list if you're interested in this topic. I hope I've kind of given a flavour here. And I suppose one sort of issue is that maybe different rules are appropriate in different cases. So some cases are where you have exactly the same evidence as your friend and equally intelligent. Some cases are where actually your first order evidence is different. It might be similar quality, but it might be different. And so there's lots of sort of complexities and subtleties involved in the topic. And so generally I'd refer you to some of the further readings if you want to delve deeper into this, in particular if you want to write a summative essay on this topic. Now, if you have any questions, as usual, please do get in touch with me, drop me an email. If you want, we can arrange an online appointment to discuss the issues. Otherwise, that's it from me for now. And I will shortly post another video of the sort of final topic that we'll discuss for this term. Okay, that's it. Bye.